It's always good to get out and share our knowledge and a little bit about H2O. So really the presentation I put together here is I got a couple slides just to do a high level overview of H2O in case you're not aware of who we are or don't know much about us. And then it's going to dive into MBR application, which is our FlexMBR, and then finish up and go through a case study. It's a good case study of where we did a retrofit, and it kind of highlights the different attributes that we've done, but also how you go about incorporating the FlexMBR into whether it's a retrofit, a greenfield, or an application to expand. All right. First, H2O, we consist of really 5 divisions. So we have a water technologies and service division. We have a specialty products where we actually manufacture specialty chemicals for RO and UF and anti-scalants and cleaners, and also provide PMOT couplings and PMOT cartridge filters as well. We do have an O&M division. We operate and maintain over 600 different locations of utilities, ranging from small little communities up to larger cities such as Houston. And then our newest division, which is our water infrastructure development division, now brings to the table, allows us to do full-blown design, build, own, operate, particularly on water reuse applications. And we tend to target industrial applications for those. And then been around since the get-go of H2O is the maple and agri-food division. Really, the synergies between these 5 divisions we think makes us somewhat unique, as they allow us to provide support throughout all phases of the project. So we can design, build, own, operate, and develop a turnkey water solution for you. At a snapshot high level, we're over 1,200 team members. We focus purely on water and wastewater treatment. That's it. And we have a very deep expertise in membranes. Every single one of us in this organization has been around membranes for, I would say, 3/4 majority of our careers. We engineer, manufacture, service, and operate water, wastewater, and water reuse systems. Through our expertise in membranes, we really promote a flexible approach and really want to provide freedom of choice to the end user and try to enhance performance and reduce overall operating cost. In terms of projects, we are obviously pretty broad in North America. We have over 800 industrial municipal systems, and those UF, NF, RO, MBRs, some small systems, and then we, as I mentioned, we operate over 650 water and wastewater utilities. So we take that experience from O&M, we can apply that into a lot of our technologies and designs as we're looking at water and wastewater plants. And then we are an OEM. We have 2 manufacturing facilities. It's over 100,000 square feet of manufacturing. We have a facility just outside of Minneapolis, and then we also have, as I mentioned, a facility in Quebec. So we can cover Canada and the US quite extensively. We do have chemical mixing and manufacturing in Vista, California as well. And we have full-blown engineering. So we have in-house process, project mechanical, electrical. We do all the instrumentation and controls, and then full project management and project execution. But having that in-house ability, so we build all our skids from the ground up, and it really gives us a firm basis and ability to test and check them out before they ship to the site. Try to save time on site. All right, so that's the overview of H2O. I'm kind of sped through that, but so I will move into the MBR portion of it. And I wanted to start first by just kind of going through kind of the key applications we look at for MBR, and I've kind of categorized it into three categories when we're looking at this. First, obviously, is stringent effluent limits. So with MBR, you have the capability of getting exceptional water quality because it is a UF membrane in the end. It is a barrier. So when folks are looking to get BODs and TSS less than 5, trying to get less than 10 on your nitrogen, and then total phosphorus less than 0.3, MBR is a good option for that. Also, simplification of the plant process, so it's a little less reliant on biological settling and can eliminate a lot of those multi-steps in the unit process. So I'll move on to that next, but really you can eliminate, whether it's an additional clarifier, you may have a disc filter that's doing some polishing in the end. There may be a slightly higher capital cost on MBR portion of it, but generally you're eliminating steps in a traditional conventional wastewater plant. The other factor we look at is if a plant's looking to increase capacity. You can get a much more compact footprint with MBRs, double, maybe triple the capacity of a conventional activated sludge facility. And it's also very adaptable to retrofit into an existing treatment plant, whether you're trying to expand the plant life, extra capacity, or hit new treatment goals. And we'll touch about that in the case study. This is actually a picture of the case study we'll be touching here at the end. And then when you have seasonal and variable flows, or surge flows, because MBR is a barrier, you are running at higher mixed liquor concentrations than you would with a traditional. You're able to handle certain high flow loading better than a conventional system. Tends to be a little more robust on the biological side. You can build a portion of that equalization into your bioreactor because you are running at that higher mixed liquor concentration. And because it is a membrane, you can run temporary flux increases that handle some of those short-term surges that a plant may see, and run the flux a little bit because you're able to clean them back, get them back to a condition where you can run that MBR at a nice steady state. So want to dive into the FlexMBR platform that we have developed our MBRs for. First, a little bit of a history. In a nutshell, MBRs have kind of gone through what we would consider 3 membrane lifetimes. When MBRs first came out, it was 3 products. It was Xenon, it was Siemens, and Kubota were the three main players. That has now since grown to over 30 different products and continue to grow in this day as the MBR kind of took foothold and got adapted more and more within the market. And that brought obviously increased competition, technology matured, it improved, really new products that have been developed, positioned for that retrofit market of, those first membrane lifetimes where those first membrane systems were installed. So based on that, we feel the current market allows for a flexible MBR system. And to kind of talk what we mean by that is we'll just start real basically. In a biological treatment system, you have your bioreactor, your biological treatment, and then you have your solid separation. The feed coming in, you'll have your return activated sludge, and then you have your effluent or permeate going out. So that solid separation typically is a clarifier, some sort of sedimentation, or it could be a membrane. So from an MBR process, we're going to focus on that solid separation. So the reality is you have that membrane filter you drop in within your tank, and you have your activated sludge from the bioreactor coming in, you have your return activated sludge coming out and going back to that bioreactor. And the membrane, you pull a vacuum on it, and the permeate comes out, and you're concentrating that sludge within the tank. So with that factor, on a membrane system, you're going to have a permeate line coming off. As I mentioned, there's a vacuum, and then you're going to have an air supply coming in. That's supplying air scour for that membrane to keep the solids from building out, impacting to a kind of an irreversible fouling or flux condition. And with that, really, it's that membrane filter. Traditionally, has always went to a membrane supplier, and they design around their system, around their membrane. But the reality is, there's enough systems out there, and in our expertise, we found that really your permeate, your air supply, how they run those and set those can fall within a common band. So that allows you to maintain these conditions and provide flexibility in that pump, the air supply. That gives you that flexibility to drop in a different membrane, whether it's hollow fiber, it's a flat sheet. or even ceramic types applications. So that's our concept at a high level. It's simplified from what a flex MBR is. It gives you that flexibility to use a wide variety of different types of membranes. So with that and this whole product convergence of a wide variety of manufacturers, when we're looking at a flex MBR design, really the considerations we're looking at is the air scour rate, the mixed liquor concentration, what kind of process sequence is coming in, and then obviously there's module dimensions. So every module's got a little bit different dimensions, and how do you make that fit in so you can adapt to keep that flexibility? And what we found out is really as memory manufacturers operate within similar bandwidths. And because of that, we can target and design and accommodate several different manufacturers through our experience and knowledge, and really comes into that the heartbeat and programming of our systems. But if you look, for instance, at air scour, we can find a band where we can get the aeration module and size a blower for that and add a VFD and provide the programming and knowledge behind that to accommodate a wide variety of different manufacturers. Same thing in the mixed liquor. Generally, you can see from this that your bandwidth is going to be somewhere between that 7,000 and 12,000 milligrams per liter in the mixed liquor concentration. So that gives us kind of an overall scope that we can target. And same thing on operating sequences. In the MBR, there is a permeation and a relax cycle. So typically, you can see here, folks are permeating anywhere around that 6 to 10 minute time frame. With relax cycle, it's anywhere that's pretty standard, either from 30 seconds to 1 minute. So taking that knowledge and kind of where that optimal operating band allows us to really build an MBR platform that we feel can be flexible and adaptable to a wide variety of different membranes. So really our platform starts with a membrane module cassette. They come in different sizes. So with that, we developed a universal module support platform where we can drop different types of membrane modules within a system, within that platform. And then the other key part of it is a flexible control system. So we've taken all that knowledge from our years of experience and put that into our program and allow us to adapt and change settings within the program to accommodate different membrane manufacturers. And we don't lock that program. We feel we have that open source concept. So our programs are open. You don't need a special code. We provide that to our end users so that adjustments can be made and programming details can fall within their individual controls teams as well. And then we're pretty flexible on ancillary equipment. A lot of times we'll provide those blowers. We'll size them if they got particular vendors that they want to use. Generally, we can accommodate, but we like to go through that selection process and select that just so we know that's going to fit within our control and our FlexMBR platform. And then there's flexible air and permeate connections to the tank that allow us to accommodate the different membranes. So really, our FlexMBR platform, it is an open source design from the controls on up to the equipment, where we want to have flexibility to select the membrane, flexibility to change the membrane down the road for whatever reason it is. And there is a lifetime of membrane, so you want to be in a competitive situation. That certainly helps get best price for the end user. And then as we mentioned, it's always evolving. So there's newer technologies coming up all the time. Allows you the ability to down the future to be able to accommodate that and use multiple projects. I mean, here's a perfect example. You can have multiple different modules within parallel trains in the FlexMBR platform. Always like visuals. So this is actually a visual from our pilot, and you can see we've got two different membranes side by side. We've got a Hydronautics and a Toray in one, and then a Sumitomo hollow fiber, and then a Medesha flat sheet. Our pilot does accommodate up to three different membranes if folks want to test or validate or optimize a membrane in that selection process. All right, so wanted to go through case study. It's a plant we did in 2019 in Decatur, Arkansas. It was an existing SBR. They had a couple things that they needed to accomplish. One of the big ones is they needed to increase influent flows as they had increasing demands, not only from the community, but also industrial flows that were coming from a chicken processing plant were increasing as well. So they needed to be able to double their capacity. The other neat little caveat is because it's an operating plant and it's for the community, they had a retrofit without taking it offline. They need to be able to process the sewage coming in to the community. And then maintain the same footprint was a key factor, as well as they were limited on space. Yeah, there is some green space, but that's in the surrounding. You can see in this picture here, but it's more for being able to have, there's other future expansions outside of this core footprint right here. And then obviously they had needed to meet effluent criteria as they were discharging to I think it was a small river, creek, I can't remember, but they needed to have a good effluent quality. So with that, we did bid against outside of us. It was a competitive bid with GE, Vivo, Fibercast, and Evoqua as the other bidders. We ended up being low cost, but we also proposed an innovative solution, kind of out of the box thinking of how to maintain within that same footprint and not having to add a new building or additional structures to the side of the plant. And I'll talk about how we did that. And then how we were able to conduct a retrofit without taking the plant offline entirely, be able to maintain flow through a couple trains. So these were kind of the key criteria in our selection for this. And I'm going to go through a little bit of that project here. It's going to be lots of pictures and details. Feel free to cut in whenever you'd like. So we had a pre-existing 2.2 MGD SBR plant, essentially 3 trains of SBRs. You've got your wasting over here. This essentially is your EQ. And they had a post EQ over here. And then what you can't see is kind of their filtrate. Oh, it's over here. I think it's a filtration building as well. So the intent was we need to increase the flows. So there was kind of what we went through 3 stages to accomplish this. We initial startup was for 2.2 MGD, and we did this by essentially commissioning. We had 1 MBR train and we had 1 SBR train operating during that stage 1. While we took the second train off on the SBR and doing the work inside that tank to accommodate it. Stage 2 was essentially getting that second train MBR going. And then stage 3 is we had all 3 MBR trains going through to get that 4.6 MGD build out. As I mentioned, there was some high strength from the chicken processing plant that kind of gave us increased COD in there, 400, 600 range. Some TCAN ammonia was also elevated than your traditional straight sanitary sewage as well. And then these are the effluent parameters that we had to meet. So we had to get less than 10 in the BOD, less than 15 in TSS, no TKN, ammonia down to less than 1.6, obviously nitrates less than 10, and then they had a total phosphorus limit of less than 0.1. All perfectly suitable and adaptable to NBR, with that barrier providing a lot of that, I guess, security to get these effluent criteria. So from a retrofit standpoint, 3 real key things. We needed to meet the design requirements. We had to provide an economic approach, and we absolutely had to allow the plant to keep operating, which proved to be a challenge, but it was a fun challenge, and that's what makes this particular case study and project a good one to talk about. So essentially, as I mentioned, we had a pre-existing plant. each train was 3/4 of an MGD, going from EQ through our basins to the SBRs, and then we had a post EQ as well. They did have disc filters within this building to do final polishing before it went out to the environment. Overall, the retrofit plan was we needed to add steel membrane tanks and membranes on top of the post EQ. So that was when we're saying we're thinking outside of the box. So we proposed having an elevated MBR tanks, and it actually allowed us to use some gravity flow and not having to use those permeate pumps all the time and use gravity to our advantage. But it also allowed us to be able to keep that plant operating as well and install the RAS overflow lines. We leveraged the filter building for the MBR equipment and permeate tank. We located them within there, and then we did a train by train startup to keep the plant online. So at a high level, those are kind of the 4 key steps within this retrofit. So the first step was to install structural platforms across that post EQ. This is where we're going to locate the individual membrane tanks for the 3 trains. And you can see here, plant still operating. Started installing that structure in the girders to support the membrane tanks. The membrane tanks were manufactured within our facility outside of Minneapolis. Everything done, tested, fit up, and constructed in there before bringing it to the site. After that platform was done, we went through and installed both the RAS piping and the permeate piping within the facility. And you can see here's a platform. We've got the RAS piping being installed. We still have got the operating plant at this time. This is what it looked like when it was completed and all installed and in place. And then we needed to install the permeate storage tank and the permeate pumps within the building. And you can see it was a pretty tight fit, but we were able to manage it. So we got that permeate storage tank, and we got our permeate pumps within this building. Everything was pre-skidded, pre-wired. We just dropped it in, tied the connections into the junction boxes and the piping. You can see where the plastic piping is. That was the piping that was added and accommodated along with the valving, including the flow meters, some of those ancillaries that we provided as well. And once that was installed, the next step was to install basically submersible feed pumps. So these are the feed pumps to the MBR tanks. We located 2 in each of the tanks. And you can see here, we've got a picture here of those feed pumps installed when one of the tanks was down. Worth to note, we also did, as we went through our calculations, because we do have a higher concentration of mixed liquor, we did have to add an additional generation header. There was 2 initially. We added a 3rd to maintain the appropriate aeration needed for the aerated anoxic process that we installed to feed into the MBRs. The next step was to install those membrane air scour lines from the blowers. We initially looked here. Ultimately, these were existing blowers for the SBRs. We ended up locating the blowers over here to accommodate those lines. Kind of the same, similar in terms of run lines. It was also closer to where power sources was and that filter building. So I see, yeah, you can see these are the Erickson blowers that we installed here for the air scour, along with all the lines ready to go and make those final connections. And then the next step was to place the prefabricated membrane tanks. As I mentioned, these were designed by us, fabricated in our Minneapolis manufacturing facility, with the intent of being able just to drop them in, crate them in, and drop them in. You can see here the installation, pulling one of those tanks off right now to be dropped onto that platform. You can see the lines, and we shipped the headers, the permeate and air scour headers. That also came from our shop. We shipped those loose, and they were attached on here once membrane tanks were put in place. You can see that here, the attachment of the prefabricated permeate headers, so everything was fitted up in our shop, decoupled, and then shipped to site. So once we had one undropped, we added those permeate air headers onto the system. And then the next step, once that was in place, everything was connected from all the piping perspective, was to start converting these trains to MBR in sequence. So we did one train at a time while maintaining operation of at least one SBR train to keep that flow that was needed. So as you saw earlier, it was the initial stage was 2.2 MGD, so it's kind of maintained the initial flow plus a little bit more, and then increase that with each MBR train being brought online. And you can see overall we did that. So here we've got the one tank down. As I mentioned, we dropped those two submersible feed pumps. We also added a third generation header into the tank. And then we also did have to provide the defined screens with the MBR. We need at least a 2mm screen. So we added those, we sized those, provided those in order to get that in before it drops into EQ. That was the other step that I did mention earlier, but was added. This gives you an idea of what those FlexMBR membrane frames that can accommodate. In this case, these were hydronautic hollow fiber membranes for the Decatur plant. That fits in this frame. So that's the interior frame here for those hydronautic membranes. So all the frames were brought to site, membranes are shipped, and we did this at one train at a time. So we installed the membranes in, and then we raised them and dropped them into that first tank. Once they were installed, went through obviously wet with clean water, process it, make sure everything's functioning, everything checks out, we're good to go. Once the thing was functioning and got the okay from a commissioning standpoint on the clean water, we introduced, this is obviously the full plan at the end, but we introduced wastewater into that first train to get it going, get it optimized, fully commissioned and running. And at stage one, we got that 2.2 MGD. We brought on the second train to get 3.8 MGD while still operating one SBRs. And then once we had these two trains going, that gave us 3.8 MGD. We're able to take down that final SBR tank, empty it, install those two submersible feed pumps, install the third SBR air header, and then get that one going to get a full functioning 4.6 MGD plan in the end. So that is kind of the pictorial snapshot history of how that retrofit took place while maintaining operation of the SPR plant and feed into the facility. So that conversion, as I mentioned, was completed in April 2019. So exactly 6 years, almost to the day. Plant flow rates increased from 2.2 to 4.6 MGD. We did it within the same footprint. And in the end, we're producing excellent effluent quality. BOD TSS for non-detect, nitrate was less than 5, and the phosphorus was less than 0.5 MGD. So we hit all those criteria, and to this day, the plant is still operating in that nature. Actually, we're actually going through another I guess, upgrade or retrofit there at the facility. We're actually on the waste, we're actually using membranes to thicken that sludge a little bit to accommodate the capacity within that waste tank, so that it can handle more solids. They're having to continually process it a little bit quicker, but by thickening that tank, we're using membranes to do that as well to give them some additional capacity within that footprint. And then a key thing, one of the big things, which I didn't mention, was the controls. They had no overall SCADA or training within this plant. So we programmed and installed our Intellex SCADA system, where we've given them full training of any of their water analysis. All their water analysis gets fed into here, so we can get training of that plant. They can maintain each on a train by train basis. This is all within, that was all part of the overall design and incorporating all those features and parameters to accommodate the different conditions. And this platform will allow them, if for some reason they want to switch to a different membrane in the future, they'll be able to do that with this program and accommodate those changes on the permeate pumps, the blowers, and a lot of those set points that we've pre-programmed and put in the background for them to accommodate that. And that's it. That's a little bit about the FlexMBR. That's the case study at Decatur. I hope that gave you an idea of what can be done. A little history around the FlexMBR, but I'm open to any questions at this time.